Hi, my name is Chandler Watson. I'm applying to the PhD program in mathematics at the University of Washington, and this is my 5-minute talk on the Cayley-Hamilton theorem. So we're going to start with a vector space V, which is a complex vector space of finite dimension. We're going to take a linear operator on V and say it has eigenvalues lambda 1 through lambda n, with multiplicities d1 through dn respectively. We can make a definition, and that is that the characteristic polynomial of T is just the polynomial with roots being our eigenvalues and multiplicities being the multiplicities of our eigenvalues. So this polynomial has a lot of great properties, but in particular, the Cayley-Hamilton theorem says that if Q is this characteristic polynomial, then Q applied to our original operator is equal to 0. So why might we care about this? Well, let's see a quick example. Let's say we have a 2x2 matrix here, and we want to compute A inverse, but we've forgotten the formula for the inverse. Well, first, we can compute our characteristic polynomial. So eigenvalues are -1 and +7. And so this means, by Cayley-Hamilton, that Q of A is equal to A squared minus 6A minus 7I, and that equals 0. So rearranging a bit and factoring out an A, we can see A times A minus 6I over 7. Here, 3 multiplied by A is equal to I. And so in fact, we can see right away that this is our inverse. So how might we prove this? Well, we're going to recall some results from any standard textbook on linear algebra, say Axler. Recall that G of lambda JAT, our generalized eigenspace, is a set of all V such that, well, if this were the standard eigenspace, it would be T minus lambda JI times V is equal to 0. But because it's generalized, we consider any exponent of this operator. Moreover, G has a nice decomposition into these generalized eigenspaces, and in fact, it's just a nice direct sum. Lastly, we recall a standard lemma that if T is an operator on a finite dimensional vector space W that is nilpotent, then in fact, T to the dimension of W is equal to 0. So let's dive in. Using these results, we note that by definition, T minus lambda Ji restricted to the jth eigenspace is nilpotent because every element eventually becomes 0. Thus, by part C, we have in fact that T minus lambda Ji restricted to the jth eigenspace, so the dj must equal 0. So now our characteristic polynomial applied to T can actually be rewritten in a clever way. We can take the part in the middle, that is the jth term, and stick it at the end. So we can rewrite it with T minus lambda Ji, so the dj at end, meaning that our characteristic polynomial restricted to the jth eigenspace is equal to T minus lambda Ji restricted to that eigenspace raised to the Gj power. But that's just 0. And so by part B, we note that our characteristic polynomial is 0 on each part of this direct summand. And so it equals 0 on the whole space. In other words, Q of T equals 0. And there we have it, an example and a proof of the Cayley-Hamilton theorem.